Okay, so with that being the case, with no further ado, I want to go ahead and introduce our guest speaker for today. I'm very excited, or we're very excited to introduce our guest speaker today, Dale Decatur. Dale is a PhD student at the University of Chicago, and Dale is a member of the 3D lab, or 3D lab at the University of Chicago, and he'll be presenting today on text-driven localization and local editing of 3D shapes. So with that being the case, with no further ado, I'm going to go ahead and segue into Dale. Take it away, Dale.
Awesome. Well, yeah, thank you so much for that introduction, and thank you so much for having me here today. Super excited to be here. I'm just going to share my screen real quick. Okay, yeah, so today I'll be talking about text-driven localization and local editing of 3D shapes. So, generally in today's world, 3D content is widely used in many fields, such as manufacturing, engineering, virtual and augmented reality, medicine, and entertainment. And because of this, the demand for, tools that can sort of create and manipulate 3D content is growing faster than existing techniques can really support. And then if you actually look at our current tools that we have right now, they're actually sort of somewhat inaccessible and hard to use as well. So first off, they require a significant amount of time and experience to learn how to operate. So you have to actually learn how these things work and, sort of train in being able to use them. And then even once you've sort of invested this time into how to use things like Blender or other 3D modeling software, actually creating and manipulating these 3D assets takes a lot of manual effort and input along the way as well. So it's definitely, not an automated process, and it's sort of a little bit, harder than we want it to be. So we sort of need a better way to be able to work with these 3D assets. And, one solution that people have looked towards is text. Text guidance. And, why is text guidance such a good medium? Well, first off, it's actually quite intuitive to use. So most people are capable of describing whatever 3D edit or 3D creation they want to make with text. They can sort of just, use natural language to do so. It's somewhat straightforward. Another thing that's nice about using text is that you can be very specific and precise with your description. So maybe there's some, subtle nuances that you want to get across in your edit. Well, you can just, add a few extra words to sort of describe those components and be able to add them to your edit. And so, we are by no means the first people to work on text-driven 3D content creation or content manipulation. So there are many recent works that focus on global 3D generation and stylization. So things like text-to-mesh, latent nerf, dream fusion, the list goes on and on. There's lots and lots of these works. But the key thing about these works is actually they're all designed for, in the most part, global generation and global editing. And these works don't really support local edits. So, why is that important? Why do we care about local editing? Well, oftentimes users will want to change very specific aspects of their object while preserving its overall identity. And this can be important for things like model personalization, which is becoming more and more popular, where you maybe tailor some generative model to a specific person or object. But that's just one example. A lot of times you have this preference to sort of not lose the overall identity. And what we mean by that is saying okay, if we have some edit that we want to make, we don't want to change things outside that edit, because then we might sort of lose the components that make the object, that object to start with. So if you look at the example we have sort of at the bottom of the screen, we're showing a very specific teddy bear. And the idea is we want to add, let's say a blue apron to this teddy bear. Well, we only want to edit things in the apron region, because if we start editing the rest of the object, we'll sort of maybe we'll get some generic teddy bear with an apron, but we don't want that. We want this specific teddy bear. So that's sort of the idea behind local editing. You want to be able to preserve the identity of the original model by only editing a very local region. So yeah, so what's the vision, right? So the idea is we start with some input mesh, and then we also have some text prompt that describes the edit we want to make. So here we're showing, a mesh of a cow, and then we have the prompt, a gold chain necklace. And the idea is we want to be able to figure out, first of all, where do we add this necklace on the cow? And then once we, are able to figure that out, actually we want to add it in a high resolution way. And as we just talked about, we want to only edit this one region of the necklace and leave everything else unchanged. So this is just, one of the results from our paper. So today we're going to discuss two works that sort of address this task of local editing. So the first work is 3D Highlighter, And this sort of sets the foundation for the local editing task by being able to do text-driven localization, basically figuring out, based on some text, what portion of the 3D object best corresponds to that text. And then the second work is 3D Paintbrush. And this is sort of expanding on that first work and saying, okay, not only do we want to do localization, how can we do local editing as well? But before we get into these two works, I wanted to give a little bit of some background on how we do 3D supervision, and specifically, how we do so using 2D pre-trained models. So if we're looking at, the comparison between 2D and 3D models, well, so deep learning has shown great promise for 2D image synthesis and 2D image editing. This image that I'm showing on the right is from Stable Diffusion, for the prompt, an astronaut riding a horse. And as you can see, the image very closely respects the prompt, the astronaut's on the horse, and also it's very good quality. So it's like high resolution, and it looks really nice. Unfortunately, for 3D generative models, they're sort of like fundamentally limited compared to their 2D counterparts. And the reason for this is because we just don't have nearly as much 3D data as we do 2D data. So if we try and train some 3D model for like a similar task, we're not going to have the same ability to sort of generalize, and also the quality is going to be poor. So that's sort of the issue with the current state of the art in like purely 3D models. So, how can we fix this? If we want to do some kind of like 3D optimization and we don't have a 3D model, what can we do? Yeah, so how can we deal with this? So, one idea that a lot of people have been using recently is to do 3D supervision from 2D models. So the general idea is, let's say you have some 3D representation. In this case, we're showing, a textured mesh of a donut. And the idea is, okay, we have this 3D representation. And then what we're going to do is we're going to differentiably render this 3D representation into a 2D image. And then once we have that image, we can do some sort of procedure using some pre-trained 2D model to supervise, given some text, that 2D image. And the idea is, like, if we have some way of getting gradients for the 2D image, because we differentiably rendered it from our 3D representation, we can backpropagate those gradients for the image all the way back to the 3D representation. And that's sort of the common approach that a lot of these methods use to optimize their 3D representations using 2D models. And one really nice thing about this is that we don't need any 3D data at all to do this. So because we're training using a supervision from these 2D models, those 2D models are trained entirely on 2D data. So again, even though we don't have a lot of 3D data to train on, that's not a problem because we're using these 2D models. So now that we've gone over some background, I'm going to go into the first paper. So this is 3D highlighter, and this is about text-driven localization. And this was a joint work with Itai Lang and Rana Haneke. So, what is this paper about? So 3D highlighter localizes semantic regions on a shape using text as input. So here we're showing some examples. So we localize the region poncho on a horse, necklace on a human, or headphones on a bunny. And what's the motivation for this? Why do we care about region localization? Well, for one, as we've just sort of been talking about, it's important for local editing. Additionally, there are many tasks in 3D modeling that need to be applied locally, like geometric edit. So maybe you want to move some part of a mesh around, but you only want to do it to a local region. So identifying that region is important as well. And sort of just more generally, if we have the ability to perform 3D localization, this opens up many possibilities for local semantically aware geometry processing and just general processing of 3D shapes. So why is this challenging? Well, for one, as we sort of just talked about, there's not really enough good 3D data to be able to train some model for open vocabulary segmentation or localization. The standard approach of just using data to train some model isn't really going to work very well for this task. Additionally, a lot of these localizations that we're trying to find don't have a lot of geometric signal. So here we're showing the localization of a belt on a dog. And as you can see, the actual region we care about is quite similar to the regions around it. So if we're using some more analytical approach that isn't maybe database, but just looks at the geometry of the object and local differences, there's not much information for those approaches to go off either. So again, this is a challenging problem. And then how about our task specifically? Well, one thing, we want to be able to have our method work on low quality meshes in the wild. So, these meshes might be non-manifold, they might have boundary, they might have self-intersections. Additionally, these meshes, like we said, they're not from some data set, so they might be from some non-predefined category. You might have some very weird, nonsensical mesh that, a pre-trained model wouldn't have seen before. So you have to be able to generalize to that. And then also you have this potential mismatch between the localization region and the object you're starting with. So like here we're localizing a hat on a candle, and obviously, candles don't wear hats, but, humans are able to sort of generalize, and we want our model to be able to generalize as well to give like some kind of reasonable result. So what's the key idea behind this approach? Well, we try and use analysis via synthesis. And in this case, this sort of corresponds to extracting analytic information implicitly contained in the generative process. So if you look at a lot of these text to 3D approaches, here we're showing a result from text to mesh. You can see, if we have, Steve Jobs, it has like the facial hair on the lower part of the face. There are shirt folds that are, quite like believable. There's also like pant creases in the thighs. So what these results are sort of showing us is that a lot of these generative models are sort of very clearly demonstrating a global semantic understanding, right? Because that's to know, like, where the torso is so it can put the shirt in the right region. That's to know where the pants are, the face for the beard, things like that. So, like, there clearly is this global semantic understanding. And then the question becomes, well, these models are explicitly, designed for generation, but like, and there's no explicit way to segment these regions, but like, is there some way we can tease it out from the model by sort of like cleverly like formatting our generative loss? Right. So the idea is we're going to take our analytical problem of region localization and reframe it as a generative problem. Because again, we know how to do these generative losses, using the techniques we just talked about. So yeah, so how do we actually go about doing this, right? So, in a lot of these generative approaches, we'll sort of simply start with a 3D representation, and then we'll style our mesh by predicting colors over the surface of the mesh. We'll use some like neural field. And then, our idea is we're going to say, okay, instead of just predicting colors, we're actually going to predict localizations with our neural field, and then we're going to color the mesh entirely based on our localizations. And we'll get into why that's important in a second. So yeah, so how does our thing work? So we start with our mesh. Here we're showing a cow, and the idea is like, okay, we're gonna take in points on the surface of this cow, maybe the vertices, so XYZ coordinates, and we're gonna have some MLP, which we call our neural highlighter, which is going to predict, as we just said, a localization probability for each of these points in the mesh. And what this gives us is like, if we're going to pass in the vertices to this neural highlighter, this will give us an explicit, segmentation probabilities for each vertex. And the question becomes, okay, if we have some way of predicting the localization probability for each vertex, how can we actually color our mesh in the way we want based on these probabilities? So what we do is we compute this probability weighted blend. So what this means is for a given vertex, the higher the probability. Oh yeah, so just to clarify, by the way, these probabilities, these localization probabilities correspond to the probability of that vertex belonging to the localization region that we care about. So here we're maybe thinking about, the localization region hat. So again, like the higher the probability of that vertex belonging to hat, the more yellow we'll color it. And then similar, the lower the probability, the more gray we'll color it. And this will sort of give us our continuous blend based on these localization probabilities. But then the question becomes, okay, well, why does this actually give us good localizations? Well, the idea is that, these generative approaches are very good at, stylizing some mesh. So the idea is if we can convince our generative, use our generative loss to style our mesh with like a yellow hat and a gray body, because the colors are entirely dependent on our probabilities, in order for the yellow hat and the gray body to look good, that means our actual underlying probabilities are looking good. And that's sort of the takeaway that we want. So how can we actually supervise this process? So it's very similar to the stuff we just talked about. So once we have our 3D representation of our colored mesh, we can use a differentiable renderer to get multiple views, 2D images of our 3D mesh. And then we're going to use some 2D pre-trained model to supervise this process to correspond to whatever text prompt we want. And in this specific case for this project, we used CLIP, which is a joint text and language, a text and image embedding space. And the idea is like we can take our rendered images and encode them with CLIP's image encoder to get some latent representation. And then we can also take our target text, which, in this case, we'll say like hat highlighted or something like that. And we can encode that text to get another, embedding in the same exact space. And then we can compare the similarity of these two embeddings and then use that as a signal to update the weights of our neural highlighter, which is the thing that's predicting our probabilities, which is, again, what we care about. So and here are some of the results from 3D highlighter. So as you can see, we're able to get nice results on a diverse combination of different meshes and prompts, as you can see here from the top row. And then also, again, because they're diverse, we're able to get results on things like animals, household objects. So we're not really limited to like one category or something like that. We're able to use the generalization abilities of these 2D models. Another interesting thing that we notice is that like a lot of the target localizations don't necessarily have to match up to something reasonable for the underlying meshes. So like here, obviously, lamps don't wear necklaces and pumpkins don't have wings, but it's able to like sort of generalize and give a reasonable result, which is exactly what we want. Additionally, our 3D highlighter approach is able to localize different regions on the same mesh. So, in this example, we're showing it with a bunny, and we can see that it's able to get headphones and hat. And what's interesting about this is, they're actually, somewhat similar localizations, but there are, subtle differences. And what's nice is to see that our models have to sort of respect those differences. So, like the headphones stay on the ears, whereas the hat comes down more onto the top of the head. Additionally, our method is able to work in cases where the geometry of the model of these two different localization regions are quite similar. So here we're showing, belt and necklace and a dog. And the underlying geometry of these localization regions is very similar to each other, but they're on like sort of different global parts of the shape. And because our method is able to sort of place the belt and the necklace in different regions, this shows some kind of global semantic understanding of our method, in the sense that the underlying geometry isn't different. It's only really the global position on the shape that's changing. So that's sort of a nice thing to see. Now onto some of the applications of 3D highlighter. Well, this is sort of the obvious one that we're sort of talking about in this talk, where we can do local editing. So here we're showing 3D highlighter applied for the case of local editing. So imagine you have some uniform texture over the entire mesh. So here maybe we have like cactus over the entire shoe, and then colorful crochet over the entire horse. We can use 3D highlighter to localize a region such as laces or on the horse poncho, and basically just mask this uniform texture to this one specific region and get like sort of a local texture as opposed to a uniform texture over the entire mesh. Another thing we can do is local edit composition. So here we have 3 global stylizations for Iron Man, Steve Jobs, and Yeti from a text to 3D model. And what we can do is use 3D highlighter to sort of select different regions from these 3 different meshes and then composite them directly together to sort of get this melded, cool combination mesh. And then also we can do geometric edits. So again, once we have this localization region, we can sort of do whatever we want with it. So we can maybe stretch the vertices, we can extrude the vertices, and sort of perform whatever geometric operations we want to perform as well. So to summarize for this 3D highlighter paper, the general idea is like now we're able to do mesh localization via a pre-trained 2D model, which means that we don't need any 3D supervision or 3D data sets. We also use text as guidance, which allows us to get intuitive control over the localization region, which anyone can sort of use this approach. You don't need any specialized training. And our result works on low quality meshes, like we talked about. We don't have to worry about like boundary or self intersections or things like that. And then also, again, our approach is based on using synthesis as a means for extracting the underlying analysis. In this case, that's using the generative approach to do region localization. But the question becomes then, these models seem to have a lot of understanding. Are there things beyond localization that maybe we can also extract in the future? So our paper and code are publicly available. You can check out our project page here, as well as our GitHub from the QR code. So definitely, if you're interested, check those out. So let's move on to the next section of this talk. So, shifting from solely localization now to local editing as well. So text-driven local editing. This section is based on our recent paper, 3D Paintbrush. And this is a joint work with Itai Lang, Fear Aberman, and Rana Haneke. And so the idea here is we're going to say, okay, we've just done, text-driven localization, but is there some way we can combine this localization and texturing together to get a local editing approach that has the texture sort of respect these localization regions and conform to them? So here we show some examples. We have a stained glass turtle shell on the cow. We can also get things like heart-shaped sunglasses. I think colorful crochet hat and things like that. So, what is the motivation for this project? Well, as we've been saying all along, we want to do local editing. But if you look at the localizations for a 3D highlighter, they're actually quite coarse, and we think we can do better. So this is an example on the cow mesh from 3D highlighter with gold chain necklace. So the necklace is like roughly in the right spot, but it's sort of this like blobby, bandy mess, and it's not really the level of detail that we would want. Like you can't see like the individual like chain links, and it's not as high resolution as we would want. Another thing is that we want to be able to learn our texture as well. So when we were showing local editing applications with 3D highlighter, we were starting with some global uniform existing texture and then just sort of masking it with our localization region. And that's great, but if we want any kind of local edit that doesn't involve a uniform texture, that sort of falls apart because there's no way to ensure that the texture really matches up with the localization region. So we want to be able to learn our texture too. So why can this be hard? Well, first of all, we need an efficient and compatible method for storing the edits. So for that, we use texture maps. I'll get into a little bit more on that later. We also need to ensure that only the desired regions are changed. This is sort of what we were talking about in the beginning, where we don't want to lose the identity of the underlying object. And to ensure this, what we do is we have this explicit localization region. So very similar to what we're doing in highlighter, if we have some explicit localization region throughout this learning process, we can ensure that the edits are contained to that region and don't really change things outside of it. Another thing is we need to make sure that the localization region and the texture edit match up. So here we're showing an example where they don't match up. So if you have this localization and then this like sunglasses for the texture that are ever so slightly shifted over, when you go to mask them, you sort of get these weird artifacts because they're not lined up properly. So that's an important thing we need to make sure happens. And then also we need to make sure we have fine-grained enough supervision to be able to enable sufficient detail for our small changes, right? So when we're doing these local edits, a lot of times we're editing very small regions in the mesh. And because of that, we might care more about the resolution of our supervision than we might for standard generative approaches. So we need to make sure we have high enough resolution supervision. So yeah, so moving on. So, why do we use texture maps? I mentioned that earlier, right? So for one, texture maps are compatible with existing graphics pipelines. So, a lot of people working with meshes and things like that will want to use texture maps for rendering to fit in with their existing tools. And then, and this sort of goes hand in hand with that. One of the reasons they're so popular is because they're very computationally efficient for storing high resolution colors. So if you look at this example to the right, we have a somewhat low resolution mesh of a mushroom. And then we have a UV parameterization that maps the 3D surface to the 2D plane. And then we have some texture map in this 2D plane that sort of describes the color of the surface of the 3D shape at every point. And what we can notice is that the resolution of this texture map is much higher than the resolution of this mesh. So what that means is that you can have points that are sort of like in between the vertices of this mesh, but actually have very high frequency details in the texture because you just have a high resolution texture map. And that's really nice because if you were, instead of using a texture map, maybe coloring this mesh just using like per vertex colors, in order to have the same level of resolution, you need to have a much higher resolution mesh. And that's actually quite, computationally expensive to work with. So it's much easier to just have a low resolution mesh and then a high resolution texture map. So you're sort of like making these things independent, which is really nice. Now, as good as texture maps are, there are some drawbacks to using them. So one of them is that you can have 2D discontinuities in the UV texture map. So the idea is like if you have 2 points that are close together in 3D space, when you map them to the 2D plane, they might be far apart. So, one example would be like a point on the underside of this mushroom here, and then a point on the stem of the mushroom. In 3D space, they're actually quite close together. When you map them to the texture map, one's on this thing and one's on here. So they're actually, far apart now in 2D space. And, why is that a problem? Well, that can actually lead to seams in the color. And the reason for that is because, maybe, the color here is ever so slightly different than the color here. And then even though they're, in 2D locally smooth. When you map them to 3D, things that were far apart are now close together, and you can sort of see this like exact seam between the different colors. So that can be a problem if you want like, smoothly varying textures. So how can we try and fix that? So one thing we do is in order to color our mesh, we sort of use this like hybrid representation between texture maps and 3D. So what we do is we take all of the pixels from our texture image, which are the texels of the texture map, and we map them back to the 3D surface because we have this mapping between the surface and the plane. So once we have that mapping of those points, we can use those exact points to query our MLP, which is going to give us our texture predictions. And what that means is that our MLP, which is this like smooth function, is going to be able to take in inputs that are going to be in 3D space. So things that are similar in the input space to this function are going to be close together in 3D space. And because of that, we're going to get smooth outputs in 3D, which is exactly what we want. Now we don't have any of these like texture seam things. But again, we want to have this efficient rendering, and we want to have this like compatibility with graphics pipelines. So what we do then is like once we have these colors on the surface of the mesh, we can, because we have this mapping and we predicted colors for each of these texels, we can map them back to the UV texture map. So this might be an example of like two different triangles that were close together in 3D and therefore both green because they're on the turtle shell. But when they get mapped back to 2D, they're far apart. But again, we don't care because this is totally fine because they were predicted based on their 3D coordinates, which were actually smooth. And that's exactly what we want. So again, once we have this texture map, we can render our mesh, efficiently and in a compatible way with graphics pipelines. So that's how we do that. So here's how our overall pipeline works. This is sort of like a rough idea. So we have our input mesh, which is in here a cow, and then some text, which is going to describe like a colorful crochet hat. And this sort of describes our edit. And then what we're going to do is, for those same coordinates on the surface that we just talked about in the previous slide, we're going to use some neural network, and in this case, an MLP, to predict texture values, and then map those texture values back to a texture map. And then we're able to apply those, to our mesh if we want to, render it to a 2D image. And then once we have this 2D image, we can use what we talked about in the background section to use some 2D pre-trained model to supervise it based on our text prompt. So that's sort of like the general overall idea of our pipeline. However, for our local edits, this is actually not perfectly sufficient. And the reason is because we don't have any localization here. No enforcement on the localization. So why do we need localization? Well, if we don't have localization, then you get this result that you see on the right. So here we're optimizing for a gray polo shirt. And as you can see, it actually does give you the gray polo shirt, but it gives you a lot of other things too. So it has this sort of skin tone across the rest of the body. It has some hair, some jeans, maybe some socks. Not really sure what that is, but the idea is that like in addition to this gray polo shirt, it's also editing the entire rest of the mesh, which is not what we want because again, we might lose the identity of whatever the mesh texture was before. So how can we fix this? So we're going to do something very similar to 3D highlighter, where we're going to have this localization loss. And that's going to explicitly incentivize a visual coherence to the localization throughout our optimization. So, this is going to look familiar. So this is that same bottom branch we just talked about, but now we're adding this top branch, which is responsible for the localization. So for each point, in addition to predicting an RGB color for the texture, we're also going to predict a localization probability, just like we did in 3D highlighter. And then now what we're going to do is instead of just using the global texture that we predict for the entire surface as our texture, we're actually going to mask our texture with whatever our current prediction of the localization region is. So what that means is now every iteration of our optimization, we have some current guess of what our localization region is. And we use that guess to mask out our global texture predictions to only have texture in that one guess region. And that allows us sort of like, enforce that our localization or that our texture edits are contained to that region. And as you can see up here on the right, this is what happens when you add in that localization loss. So with the same gray polo example, it's much better. So not only are you editing just the region of the shirt you want, you actually get a better result for the polo shirt as well, because the network has less things to be responsible for, so it can focus more on the optimization of the gray polo. Another important thing that we do is we simultaneously learn localization and texture. So that's sort of this result on the left right here. So here we show that if we, simultaneously learn our localization in yellow and our texture of these pink sunglasses, we get results that match up very nicely. And, the localization is sharp, the texture is highly detailed, it looks great. Another option we could do that we don't do is to learn these in series. And, for us, what that means is we first run some kind of 3D highlighter-like optimization where we localize our region. And then once we have that region localized, we do the same thing for our texture optimization, but we then mask with that fixed, frozen localization every time. Now, the problem with this is, one, the localization doesn't get any information from the texture, which, as you can see here, actually ends up in sort of a worse localization. It's not as good as if it gets information from the texture. And then the other issue is that the texture is confined to this, predetermined localization, so it doesn't have the freedom to sort of look like whatever it wants. It's stuck having to fill whatever this localization was that it was given. So again, it's a result that lines up and it looks okay, but it's not as good as if you do them simultaneously. And then in the worst case, you can actually do them entirely independently. And this corresponds to sort of independently localizing a region and also optimizing a global texture. And then you can just sort of mask this global texture with the localization region. And this will oftentimes give you lots of artifacts because there's no real guarantee that these two match up because they were done completely independently. So there are maybe many valid ways you could put sunglasses on this, bare octopus, maybe rotated ever so slightly over. So they're both valid on their own, but when you put them together, they don't match up, and that's a problem. So we've talked a lot about our pipeline, but we haven't really talked a lot about how our 2D loss works. So we've said, we're using pre-trained 2D diffusion model or 2D models to do this supervision, but we haven't really said how. So what a lot of these text to 3D works use is they use something called score distillation sampling. But what is score distillation sampling? How does it work? So the general idea behind score distillation sampling is, well, first of all, we're using 2D pre-trained text image diffusion models. And what we're going to do is we're going to have this loss that's very similar to the diffusion training objective. So the idea behind a diffusion model is when you're training it, you have some fixed distribution of images you're trying to align your model parameters to, and you're sort of optimizing those model parameters. In score distillation sampling or SDS, you're holding your model weights fixed and you're sort of optimizing some image to be, towards the distribution of images that this diffusion model was trained on. So, what does this actually look like? So this is the equation for the SDS loss. And like we just said, instead of minimizing the loss with respect, this loss is very similar to the diffusion model training loss, but instead of minimizing the loss with respect to the model parameters, we do so with respect to the parameters of the 2D image. So basically, we're going to get gradients for this 2D image. And then, like we said before, if we have gradients from the 2D image, we can backpropagate those through our differentiable renderer to the 3D representation. So, what does this actually boil down to? In this SDS loss, it's essentially the difference between the predicted noise from the diffusion model and the sampled noise at each iteration. And here's a somewhat simplified visual to sort of just try and get a little bit more intuition about how this works. So what happens is that every iteration we have our rendered image, which we see right here, and we're going to randomly sample some noise and apply it to our rendered image to get this noisy image. And then we're also going to have our target text prompt, and we're going to pass both this noisy image and the text prompt to our diffusion model. In our case, we use DeepFloat-IF, but this is a general approach for any kind of diffusion model, or text image diffusion model. And then this model will predict some noise as an output, and then our loss is the difference between the sampled noise and the predicted noise from the diffusion model given our noisy image and our text prompt. And sort of, the intuition for, why this is a helpful loss is because, well, you want this difference between the sampled noise and the predicted noise to be small. And what that really means is that, the diffusion model is correctly predicting the noise that you added to your image. So if your image already looks like what the diffusion model thinks of when it has this prompt like turtle shell, then the noise that it predicts will be very similar to the noise that you added, because it's trying to predict the noise to remove. So, when these are similar, and that loss will be small, and that's how you sort of know you're converging. So that's some simplified intuition about why this kind of thing works. So, one thing you might ask is SDS is great, but as we talked about earlier, we want to get high resolution supervision. So is there a way to get higher resolution supervision than standard SDS, right? Because we said, local edits are, oftentimes very small, and we want to have enough supervision to be able to like make those local edits. And one thing we actually notice is that standard SDS supervises at, for deep Floyd, it's 64 by 64 resolution, which is sort of lower than what we want or really need for our use case. So, because score distillation sampling, or SDS, is so closely related to diffusion model training, you might think, okay, well, at least in the 2D case, in these text to image situations, how do people get higher resolution? And one such technique is to use cascaded diffusion models, or CDMs. And the way these sort of work is they consist of multiple models or stages stacked on top of each other. And the general idea is that each of these stages produces an increasingly higher resolution output. So the first one gets your input text prompt, and maybe it outputs like a 32 by 32 resolution. The second one gets the output of the first model, plus the text prompt again, and then outputs a 64 by 64, and you can sort of scale up and so on and so on. And that's the idea behind these cascaded diffusion models. Sort of the key idea we have here is like, okay, can we do multi-resolution score distillation, which is, SDS, but at multiple resolutions of these cascaded diffusion models. So actually, it turns out that SDS was built to work with these cascaded diffusion models, but it actually only distills scores from the first, lowest resolution base stage of the model. Which seems like, you're leaving a lot on the table, right? Like, why not use these higher resolution stages as well for your supervision? You already have them, why not use them? So to do so, we come up with this cascaded score distillation, or CSD as we call it, which is a new way to distill scores from the higher resolution stages as well, in addition to that lower resolution base stage. So, at a high level, how does this cascaded score distillation work? So in standard SDS, you would have your single rendered image. In our case, we're actually going to render images at multiple resolutions. So one resolution for to correspond to the resolution of each of these cascaded stages. And then once we have that, we can independently sample noise and compute our noisy images for each of the resolutions. So again, SDS is just going to be this top row, but for our case, we have all these different resolutions as well. And then this is where things get a little bit different. So, in SDS, you condition on just the text prompt and the current noisy image for that resolution. For the super resolution stages, we're now going to condition on, the corresponding resolution, but also the resolution of the previous stage as well, the lower resolution stage one below. And that's going to be our condition for our model. And then what that's going to give us is now we're going to be able to predict, gradients at, or predict noise and then compute gradients at each of these resolutions. So now what this means is, okay, so in standard SDS, we only have the low resolution gradient. Here we have, gradients at each of these different resolutions, and then we can combine them together and then use those as supervision in our pipeline. So in each of these cases where we were saying, oh, we have a localization loss or we have a texture loss, what that means is we're using our text prompt and our rendered image along with the CSD loss to give us our supervision. So, can we see sort of the effect of using CSD that we just described? So on the left here, we're showing what happens when you optimize for the text prompt, a fancy gold watch. And this is using only stage one, only the base stage model. And this is equivalent to just standard SDS. So as we can see here, the global understanding is pretty good, right? It puts the watch in the right spot, but the details are lower resolution than we would like. Now, if we just use stage two, the details are actually a little bit sharper, but the global understanding is actually worse, right? So it puts the watch like on the back of the hand near the fingers, which is not the right spot. So, we want to find this sort of a combination of both. So actually, what's really nice is when you use our CSD, that's using the gradients at all the resolutions. So in this case, both stage one and stage two. And that allows us to get, a watch in the correct location, but also having those higher resolution details that we want as well. And actually, we can directly compare, CSD to SDS on a couple of different results as well, and sort of like see what they look like. So here we're showing the results, on standard SDS for a colorful crochet turtle shell, a cactus base, and a tiger stripe shirt. And then we can see the same results now with our high resolution CSD as well. And what you can see is like the results are much higher resolution than standard SDS. Specifically if you look at like, the little crochet patterns in the colorful crochet turtle shell, you can see them much more clearly than you can in the SDS case. So that's really nice. Another thing is you can actually have complete control of the influence of each stage of your CSD. So in all of our experiments, we actually sort of like fix the weighting of all these different stages. So, you don't have to play with this hyperparameter if you don't want, but it's basically just saying like, if as a user, you want to sort of adjust exactly how much you're using stage 1 or stage 2 or whatever stages you're using, you have the ability to do so. And the nice thing is that actually interpolating between the weights of these different stages interpolates very smoothly as well. So on the left, we see this is using only stage 1, and on the right, it's using only stage 2, and then you sort of smoothly interpolate the weights of these two stages, and you can see that like not only are there multiple like viable results in the middle, the results actually smoothly interpolate between these two different things, which is nice to see because that's that's not really a given. So now we can sort of see some of the results of 3D Paintbrush. So we can do things like add, a bow tie to a camel, or like, a Barcelona jersey to a Lego minifigure, things like that. All kinds of cool, different, like, weird local edits. And what's nice about this is, because of our CSD, we can actually get this really high resolution results as we just talked about. So like, if you have like a Barcelona jersey, you can get these like high details on the crest, which is like, very small. And like the same thing on this like superhero cape for the dog, you can see like the actual little wrinkles in the cape, which is, nice little details that you otherwise probably wouldn't get. It also helps with the localizations being very precise as well. Like if we can see that, on this Batman example, we have like a very sharp localization of the Bat logo, and same thing for this flip flop. You get these nice precise localizations. So we can evaluate our method by qualitatively comparing to some other methods. So here we're showing against 3D highlighter, which we talked about in the beginning, as well as Satter, which is another text-driven segmentation method. And you can see, for example, on this gold chain necklace for the cow, as we were talking about earlier, like the 3D highlighter result and the Satter result, they're good, they're roughly in the right spot, but the localization region is kind of blobby or like not very high detail. Whereas in our case, we can get these like very sharp, you can even see like the chains of the necklace like in the localization, which is really awesome. And also like it seems like our localizations are sort of like better located on the shape as well than these other methods. We can also look at other text-driven editing methods and local editing methods. So here we're comparing to latent paint and Voxy. So for latent paint, our local first of all, our localizations are like very high detail, which is great, and that's because of the CSD. But separate from that, we actually feel like our localizations are like better localized as well because of our explicit localization region. And things like latent paint end up coloring the entire shape, which can, as we talked about before, end up losing the identity of the original object and the original texture it might have had. And then, for Voxy, it does attempt to make these sort of local edits, but oftentimes the edits are, somewhat, not the right region. So, that kind of thing is nice to have as well. So, yeah. As for the quantitative evaluation, we also do a perceptual study where users will rank on a scale of 1 to 5 how well the results of either our method or other methods correspond to the text prompt they were supposed to be generated with. And what's nice to see is, for instance, on the localization and the local edits in both of these cases, our method significantly outperforms the baselines. And one nice thing to look at too is that if you look at this local edits row, we show actually additionally our method optimized with standard SDS as opposed to CSD. And you can see there actually is a noticeable difference when you use CSD in terms of the preference from the user. So they actually prefer the high deals from the CSD sort of quite clearly, which is nice to see. Another thing is we can perform some more automated methods, automated metrics for evaluation. So we can compute the clip R precision, which is essentially a measurement of how similar our generated results are to the text prompt that generated them. And again, on this result, our method outperforms the baselines. So in summary for 3D Paintbrush, we are able to have this new framework that's enabling fast and smooth and seamless texturing. So we're using texture maps, but also learning our styles natively in 3D instead of 2D. We're also simultaneously optimizing the localization alongside the texture, which gives us both better localizations and local textures than existing works. And we also introduced this cascaded score distillation, or CSD, which is a new loss term, which enables higher resolution supervision for 3D text based generative tasks. And what's nice about CSD is that it's like a general purpose text to 3D loss. So it can be used for lots of other different applications to increase supervision. So you could use this with NeRFs, with Gaussian splatting, voxels, sort of, whatever 3D representation you want. You can also use different diffusion models. So it's quite general, which is nice. And yeah, so our code is available. Definitely if you're interested, check out our GitHub. You can scan that QR code there. So yeah, so definitely you should check that out. More of a summary of this talk in general. So if we're looking at, at a higher level, both 3D highlighter and 3D paintbrush. So 3D highlighter is focused on text-driven localizations on a 3D shape. So, it's the first to do localization. And, this is a good first step, but the localizations are often quite coarse. So that's, we want to do better. So that's where 3D paintbrush comes in. Now we're doing text-driven local edits, and we're able to get much sharper localizations in 3D highlighter. And we also are able to learn textures that are tailored to the localizations by sort of optimizing these simultaneously. And then, lastly, because we have the CSD, we're able to get very high resolution results, which is great. So yeah, so what's next? So, one of the themes throughout this talk has been, local editing. So we've shown how we can do text-driven local editing with highlighter and paintbrush. But what about image-guided edits, right? Like maybe you have some image that describes something that you want to make. And oftentimes, like images can be more descriptive than text even, right? An image is worth 1,000 words. That's like the saying. So how can we use images to guide these local edits? And then also, can we extend this to 3D assets as well? Because even images have some ambiguity, right? Like you don't know what the back of the object might look like in an image. So if you have an explicit 3D, asset, then maybe this can give you a more concrete thing to guide your optimization. And then one of the other themes has been analysis via synthesis. So like in the case of 3D highlighter, we're showing that we're using this generative process to extract, localization understanding from the model. But these models are very powerful. So I feel like there's probably many things other than just localization that these models are able to do that you might be able to extract in the future. So like what other properties can we extract from these models is an interesting future question. So yeah, so I want to say thank you so much for coming to this talk. I wanted to thank my co-authors, Rana, Itai, Kfir, as well as all of the members of the 3DL lab. And I also wanted to acknowledge my funding as well. So yeah, so thank you so much. I'd love to answer any questions if we have time. So yeah, thank you for coming.
Yeah, that was an excellent presentation, Dale. Thank you, especially for going into the great detail on 3D paintbrush. So I put a quick question into the chat. There might be a couple of others. Can you see my question regarding text prompting?
How does 3D paintbrush handle the variable? That one?
Yes.
Yeah. Okay. Yeah. So how does 3D paintbrush? Yeah. The question is, how does 3D paintbrush handle the variability in user-provided text prompts to ensure consistent and accurate local texturing across different types of 3D meshes? And what are the challenges in interpreting and applying these text prompts? So yeah, so that's a great question. So, as you might know, even with these 2D models, like text, prompt engineering and like constructing your text prompts is like this huge thing that people are trying to figure out, what's the best way to design these text prompts and, how to do this. So what we find is that like a lot of times what works well for these 2D diffusion models will work well for the 3D case. So, if a 3D optimization might be harder to do and like you want to see if a text prompt is going to like look good, you can oftentimes like try it for like a 2D text to image model. And especially if you're using the same text to image model that you're going to actually use for your score distillation loss, you can like try it out in that model and then see if it looks good. And that's like a very fast check. And then say like, okay, if it works here, there's a much better chance it'll work in 3D. So there's definitely a correlation between like what works in 2D and what works in 3D, which is helpful for sure.
That makes sense. I don't see any additional questions in chat. If anyone else has additional questions, you can either put them in chat or you can come off mute to ask Dale. Well, I'll sneak in a second question, Dale, while I've got a chance. So you did mention some of the next steps, at least looking forward to 3D paintbrush in particular. But I know CSD is a big improvement, over SDS, et cetera, previous iterations. But what are some of the limitations you guys have discovered, at least, in your research over the last few months or so? And what are you, planning, in the near future to overcome some of those limitations you have discovered?
Yeah, it's a good question. So, I mean, CSD is great because it allows you to use like the other stages of the 2D model, but if you're using more stages, that's going to take longer, right? So you have to do
Right.
more diffusion forward passes. So there is this trade-off between speed and resolution. So maybe some future direction that would be interesting is like, can we do this more efficiently or something like that? But I think
Mhm.
that's hard. So I don't know how you do that, but
Right.
I think that's interesting to check out for sure. In terms of the text-driven like localization part, I think like the the quality of the localizations and the ability for the model to sort of like understand these semantics is very closely tied to the text encoders that you're using. So like
Mhm.
one reason we use DeepFloyd is as our 2D diffusion models because it uses the T5 text encoder, which is actually bigger and more powerful than Clip.
Mhm.
So we actually found that like the localization part worked better with DeepFloyd than like Stable Diffusion, for instance, because it has a better text encoder. So I think like as these text encoders get better and better, things like these localization or like these like analysis via synthesis approaches will get
Mhm.
like better and better as well. So like something like Stable Diffusion 3, like I mean I haven't even tried it out yet, but like I'm very curious to see like how Stable Diffusion 3 works with this because it has like 3 different text encoders, and I think that'll definitely really help with like these using analytical extracting analytical properties through these generative approaches.
That makes sense. Okay. Well, I'm going to sneak in one more question, and this is actually about the 3DO lab. Could you tell us a little bit about the 3DO lab at University of Chicago?
Sure.
Sort of
So
what your lab does.
yeah. So we just started in 2021, and our lab sort of works at the intersection between like deep learning, 3D computer vision, and also like geometry processing. So I think like our lab is sort of split up into like most 2 different main areas. So one is like how can we apply deep learning techniques to 3D vision problems, and
Hmm.
then another thing is like okay, how can we take classical geometry processing algorithms and maybe apply deep learning to them to either speed them up or make them more accurate or more robust and things like that. So I think that's sort of like a lot of the general ideas we work on in our lab. We're doing a lot of like text to 3D, text driven, geometry deformations as well. Like what I talked about today was mostly just texture, but we're also working on projects with changing the geometry as well. So things like that. Also, there are a few people working on animation as well, like
Oh,
deep
wow.
learning for animation.
Oh, wow. Interesting. Okay. Any other questions from our audience today? Did you have anything you wanted to add, Benedict?
I think there was one in
Uh,
the chat. Sorry. Yeah.
I don't have any questions. I don't have
Okay.
any questions. The talk was it was very explicit. It was very clear to me. So I'll just have to go read the paper a bit more. That's all. Yeah. Thank you,
Okay.
Dale.
Yeah. I do see one more question from Kata, though. Kata, do you want to come off mute or do you want me to read your question for you?
I will go through it. So my question is, when you consider some images, whether it's like, is there any study that has been looked into considering a sparse views or else a dense views, and considering those views has been well distributed, because as a distribution is a prior consideration in the exploration of sampling and diffusion, right?
Yeah. So you're referring to the views of our 3D object that we're rendering and like how those are distributed and how those are arranged. Is that your question?
Yes.
Yeah. So yeah.
And
So great question.
whether it's a sparse or like dense, is there any study that has been followed up?
Yeah, so there are strategies on like how to do this. So there are a bunch of different views. So I can tell you what we do. So what we do is we render 4 different images each iteration, randomly sampled within some like camera ranges. So basically, I think it's like I mean, the exact numbers don't matter, but it's like roughly like it's 360 degrees around, and then it's like mostly top views. So it's like we don't show the underside of the object, and we allow to see the top and the sides. And one thing we found is like in previous projects we had done things where we use like clip scores to actually determine how good a view is. So like you can say like given your text prompt and a bunch of different views, like figure out which views are like best based on the clip scores. But I think like that's actually not a good like it's a really good idea, but I think like the signal isn't actually good enough for it to like work very well. So I think you almost want to like have some like manual intervention where like we intentionally don't sample views from the bottom because, like, you know, you can imagine you have like a giraffe and you look at it from the bottom, it looks nothing like a giraffe. So it's important that you actually have good views, because if you have bad views, that's going to sort of like mess up your texture and things like that. So we basically only sample from, you know, either front on or above, and then, you know, 360 degrees around. But I think like there definitely is a lot of interesting work that can be done on like how those views are chosen. And I think, you know, certain issues with a lot of these like text to 3D approaches, like the Janus effect, like the multi-headed effect, where like you end up having like a face on both the front and the back of the object. You know, I think especially when you are starting with geometry, as we are in our case, there might be more things you can do with the views to help prevent that problem. And, you know, we haven't really looked into that too much, but I think that's definitely an interesting future area to explore.
Thank you.
Yeah.
Okay, well, we didn't have any additional questions in the chat, Dale. So I think we have presented or completed our presentation.